Hey guys, this video is for trigonometry from 7.5 and for pre-cal is from 6.5, and it is about complex numbers in polar form. So the past two lessons we've talked quite a bit about polar functions. We've talked about how an ordered pair works, where instead of going x comma y, side to side and then up and down, we can go directly to a point with the rate with r and then the theta, knowing how far out to go. We also saw how polar graphs worked in last lesson. Now we're going to start learning how to work with polar forms that are complex numbers. So before we go into the polar form part of it, I'm going to do a quick little review on complex numbers. Okay, so over here we have what a complex number is. You probably learned about this in Algebra 2. And the format is z equals a plus bi, where a, the one without the letter I, is the real number, and then the b, the one with the I, is the imaginary number. So you've worked separately with real numbers, which is what we work with the majority of the time, and you've also worked with imaginary numbers, which is what you get when you have a negative inside of a square root. A complex number is when I have them both together. Okay, so an example would be like 4 plus 3i or 7 minus 2i. Okay. Now, how that works on a graph, if I'm going to plot the point of that complex number, because it is one single point, the a and the b serve as your x comma y. One fantastic thing about math is that it is always in alphabetical order. So x comes before y and a comes before b. All right. You just have to remember that a is the real number and b is the imaginary. So if I wanted to plot 3 plus 2i, I would just plot a 3 comma 2. Okay. Now, if I had negative 2 minus 2i, I would plot a negative 2 comma negative 2. Now here, if I just wanted to plot a negative 3 serves, I don't have a number with the I, so it is just a real number. So it's like if I just had an x and 0 for my y. So A's only land on the x-axis. All right. Now here I have z equals negative 2i, meaning I only have the imaginary number. I only have the b, which means it's only going to go on the y-axis, and x is a 0. Okay? Now the first thing we're going to see today, which is still a review, is the absolute value of a complex number. Now, I'm not a big fan of the title they put for this because absolute value makes you think of just taking away the negatives. What it really means to do when they say absolute value of a complex number is to find the distance from the origin to the complex number. So for example, if I was finding the absolute value of this complex number, I'd literally just be finding the distance from 0, 0 up to that point. Okay? And the way we do that, because this creates a right triangle, it's really just solving for the hypotenuse. So it is the square root of a squared plus b squared. Okay, so this should feel nice and easy. Okay, my first question here says find the absolute value of the following, and a is z equals 2 plus 4i. So my notation for absolute value is actually putting the absolute value lines around the z, and I would say square root of 2 squared plus 4 squared. Okay. So 2 squared is 4, 4 squared is 16, and then that cleans up to square root of 20. All right, I am okay with this as your answer. Don't be surprised if in a multiple choice or if you're checking the back of your textbook, they clean this. Remember that 20 is the same as saying 4 times 5, and the square root of 4 is 2, so this could also say 2 times square root of 5. Okay, so you don't have to get down to that answer, but just again, don't be surprised if in the back of your book or like in a multiple choice one day, like on an SAT, this is what the answer shows. Okay, all right, if you feel confident, pause and try and do the next two, but we're going to continue on. Square root of a, which is 1 squared, plus b is a negative 6. Some people ask me if you have to put the negative. Formula-wise, technically b does hold that negative, but because I'm squaring, this negative is going to disappear. That's why I'm always so big on putting my parentheses, okay? But yes, that negative will disappear. So I have square root of 1 plus 6 squared is 36, which gives me square root of 37. Now 37 cannot be cleaned up, so this is your only answer here. And I know some of us are hooked to our calculators. We have a little separation anxiety there. Please don't give me the decimal. Stick to your radical notation, okay? Don't put, I mean, you could put all of this in your calculator, but make sure that you are putting your radical in your answer. Now, for this last one, 7i means that I only have the b, okay? So you can count this as saying 0 plus 7i. It's like you don't have the a, so it's like saying 0 squared plus 7 squared. But you know that this part is going to cancel out anyways. So what I'm really working with is the square root of 7 squared. Now option number 1 is going to be to say, okay, 7 squared is 49, and square root of 49 is just 7. Or you could have noticed that that square root and the square cancel out. Let's get a different color. And what you're really just left with is 7. Okay, so either way that you get to that, that's fine. And that should make sense to you. I'm going to scroll back down to this image over here. Whenever I'm missing the A or the B, remember, based off this drawing, I landed on the X or Y axis. So for example, if I want to know the distance from the origin to this point, I'm going in a straight line. It's going to be exactly that number. It's going to be 3 units away. Okay, this is just to the negative direction. And this one would have been 2 units down. So again, if you're missing the A or the B, you can understand that that's just going to be your answer without the positive or negative or without the I. All right, so moving on, we're going to start to see these complex numbers go into polar form now. So let's check out these notes. So this is going to be converting back and forth between what you're used to, which we call rectangular form, which is what we just spoke about. This equation right here, z equals a plus bi. And then polar form, remember when we talked about polar form, we had the r comma theta. The equation looks like r times the cosine of that theta, plus we still have that I for the imaginary sine of that theta. Now what I have in the boxes underneath are what you're going to use to convert them. So for example, if I was given polar and I wanted to get rectangular, I would have my r and my theta, and I would plug my r's and my thetas right here to get my a and my b. And the other way around, if I was given rectangular and I wanted polar, I would have my a and my b. I would plug them into these spots to be able to find my r and my theta, and then I would plug them right into those spots. Okay? Now, these 2 boxes, these 4 equations down here, should feel very familiar. Okay? If a and b are the same as x and y, then you should remember that x equals r cosine and y equals r sine are formulas that you learned for trig in 7.3 and for pre-cal in 6.3. You just learned them with x's and y's instead. Same thing here. You had learned that r equals square root of x squared plus y squared, and that theta was inverse tangent of y over x. Okay? So hopefully that connection helps you not to feel like you're memorizing all these crazy new formulas. It's the same thing, just with different letters, because we are talking about complex numbers. All right? Now, when we go to convert these, it's going to make your life a lot easier if you can plot them first. It'll help you at least determine what quadrant you're in, and it'll narrow down your answers. So let's take a look at this first example. Okay? It says plot 3 minus 2i, then convert to polar form. So if I'm plotting that, it's like I'm plotting 3 comma negative 2. So we're going to go 1, 2, 3, and down 2. So I know that this is at least going to be in quadrant 4. Now, if I want to get polar form, that means that this right here is my A, and negative 2 is my B. I need to be able to find my R and my theta. So we said that R is found by doing the square root of a squared plus b squared. And you should end up that r is square root of 13. All right? Next, I need to find theta. Okay? Theta is inverse tangent of b, which is -2, over a, which is 3. Now, 2 over 3 is not a value in my unit circle, so I am going to have to go to the calculator for this one. All right, so if you put this in your calculator, you're putting inverse tangent of -2 over 3. Let's go ahead and put this in degree mode so it's a little easier to see. Our calculator usually gives us our radians and decimals. So I put it in degree mode, and it gave me -33.69 degrees. Now, standard form, if you remember from a previous chapter, is me having my theta in between 0 and 360 degrees. The way we do that is we find the coterminal. So I have to add, if you guys remember, add 360, and it will give me what that value is. So look at that number really quick and compare it to your plotting, okay? -33 degrees means that I went backwards 33 degrees. And then a positive 326 degrees. If this is 270, I passed 270 but did not reach 360. So those numbers should make sense with what you plotted, okay? I'm going to transfer that work over. We got that theta was -33.69, but then we added 360 to get coterminal, and that gave us 326.30 degrees, okay? So now my final answer would be filling in this r and this theta into the polar form, okay? We said polar form was z equals my r, and then in parentheses times cosine of theta plus I sine of that same exact theta. Okay? And that's it. That is, I know it's lengthy, but that is how you write the equation in polar form. Let's go ahead and check out another example the other way around. All right, so for this next one, it says plot z equals 2 cosine of 300 plus I sine of 300, then convert it to rectangular form. So if I wanted to plot this, I need to think about where 300 degrees lands, and then go 2 units towards it, okay? It's like if I was plotting in polar. So if on my unit circle, down here is 270, and up here goes back to 360, I would know that 300 is somewhere in quadrant 4, and I went 2 units towards it. So it is somewhere in quadrant 4, okay? Now, I'm going to give you 2 options for this next one. I know that this is my r, and this is my theta. It's the same in both spots, so it doesn't matter which one you use. So I can say that a is r times cosine of theta, okay? And on my unit circle, at 300, cosine is 1/2. So I'm really working with 2 times 1/2. Okay, so A would just be 1. And then B would be 2 times sine of 300 degrees. So 2 times sine of 300 is negative square root of 3 over 2. So as you can see, those 2's would cancel, just like they did up here. Okay? And this would give me a negative square root of 3. Okay? So once I find that, I can say Z is A, which is 1, plus B. B is a negative 3, so I don't have to write the plus. And then I put the I. So option number 1 is to find the A and the B separately. Option number 2 is if I distribute, so if I distribute this 2 over to both, let me do it with a red pen. Okay, you have Z equals 2 cosine of 300 plus I, and then the 2 sine of 300, which you just did a moment ago. 2 times cosine of 300, which gave me 2 times 1/2, which gave me 1, plus, and then I'm going to place this I on the back half. Okay. And then you just did 2 sine of 300 here, which was 2 times negative square root of 3 over 2, which turned this to a negative square root of 3. And you end up with the same exact answer. Okay? So whether you like, when you convert this way, to distribute, and then here you see your r times cosine of theta and r times sine, or whether you like to do it separately and plug it back in, either way is fine. Now, this should also match up with your graph that you plotted the point. Because if I have a positive and then a negative, it means I would have gone 1 to the right and then square root of 3 downward, still landing me in the 4th quadrant. Okay, so it should match up with your graph there. All right, so next we're going to check out operations in polar form. Okay, now I know this looks very lengthy, but bear with me, it is actually a very easy formula, okay? So remember that complex numbers in polar form have the r, the cosine with a theta, and then the I sine with the same exact theta. So if I give you 2 different polar functions that are complex, right? If I want to multiply the 2 of them together, I'm going to multiply the 2 r's together and then just add these 2 thetas together, okay? So these 2 numbers would get multiplied and these 2 numbers would get added, and you write it as one complex number in polar form. Next, if I want to divide 2 of them, I would just divide the r's and then subtract the thetas, okay? Now, be careful, because when I'm multiplying and adding, order doesn't matter. So if I mix up my order here, it won't matter. For division, if I mix up my order, it will mess up my answer. So make sure that whichever one they put in the numerator is the one you put in the numerator when you're dividing, and the one you put first when you're subtracting. The one in the denominator goes in the denominator when you're dividing and goes second when you are subtracting. Okay? And the last one is if I want to raise one of those polar complex numbers to an exponent. So let's say I would want to square the polar complex number. I would square the r and then multiply that number 2 to the thetas. Okay? Very easy formulas. Let's check out this first one down here. Okay? So if z1 was 3 cosine of 45 plus I sine of 45, and the second one, z2, was 2 cosine of 135 plus I sine of 135, what would I get if I multiplied the 2? Well, z1 times z2 means that I would multiply the 2 r's, so I would say 3 times 2, and then I would write cosine of the 2 thetas, which is 45 and 135, added. Okay? And then I just write the same thing with the sine. Now all I have left to do is to clean. So 3 times 2 is 6. And then 45 plus 135 is 180. And I'm done with this problem. All I had to do was multiply the 2. Okay? Let's check out the next one. All right, if you're feeling confident, I encourage you to pause the video and try these out on your own and then check the answers. But here we go. Let's see these. The next one gave me Z1 and Z2, and it said to do Z2 divided by Z1, which means I need to pick the R from Z2 to put as my numerator, and then the R from Z1 to put as my denominator. And then I have cosine of my theta from Z2 has to go first. 135 minus my theta from Z1, which is 45. And then plus I sine. And I'm going to write the same exact thing in here. Okay, and now if you can reduce that 2 over 3, do so, but this one can't, so my answer is just going to have 2 over 3 cosine, and then 135 minus 45 is 90 degrees, plus I sine of 90 degrees. Okay, let's look at the next one. They gave me Z1 and Z2. Okay, here's Z1, and then Z2 starts here. And again, we're going to do Z2 divided by Z1. So I'm going to get the R from Z2 first over the R from Z1. And then cosine of the theta from Z2, which is 150, minus, be very careful here, the theta from Z1, which is a negative 60. Okay? And then repeat it with the sign. Oh, that's a lot of parentheses there. So what I'm reducing right now is that 5 over 10, which is going to give me half. And then cosine. Here, the two negatives are going to make a positive, so I'm really adding 150 and 60, which is going to give me 210. All right. Now let's look at two that have exponents. Okay. If I give you this as my z, and I say do z to the 5th, that means I'm doing 3 to the 5th power, and then cosine of 5 times 45. And then same thing with the sine. Okay, so 3 to the 5th power, feel free to use your calculators, is going to be 243. And then cosine, 5 times 45 is 225. And then write the same thing with the sine. All right, last question for today. I give you z, and I ask you to cube z, which means I'm going to do 2 cubed, and then cosine of, my exponent was 3, so 3 times 60, plus I sine of 3 times 60 degrees. Okay, so 2 cubed is 8. And then we have cosine of 3 times 60 is 180 degrees. And write the same thing with the I sign. All right. That is it for this lesson.